diagnosis. In software diagnosis, we can in principle put sensors in that measure every single bit. Every single thing that's happening inside the computer we can know. It's not like inside a body where we have to just put some limited set of sensors. So if we measure every bit, how do we actually treat the diseases of the memory subsystem, for example? That's a challenging problem. But that's what you kind of need to do if you're trying to understand how do you get to sort of biological immortality. That's one of the things you have to be able to do, is to figure out this sort of a basic science proxy for that problem is sort of the fixing the diseases of a software system. So anyway, long answer to the question, but please. Another. Yeah, please.
I wanted to know, is there any open source features and user private program and put it in website, then you can download and use it like an extension, something or something, or library maybe.
Right. So many different answers to that. So our model of life is to build software that ultimately we sell to be able to build more software. We use a lot of open source kinds of components, but our goal is to make a sort of coherent system that we build over the course of a long period of time. Many things that we build, we actually give away for free. So, for example, Wolfram Alpha is a free website. The Wolfram language, there will be a free way to write programs in the Wolfram language on the web. You'll even be able to deploy, you'll even be able to do a small amount of deployment of websites, the computational websites that you create from the Wolfram language for free. So that's kind of one part of it. Then in terms of being able to embed this in other systems, the idea is that our cloud can easily be called from a lot of different kinds of systems. So you can create an instant API that runs in our cloud and can be used by other systems. And when if you're, like, let's say you're making a game or something, then you could, if you have a small number of copies that are going out, you'll probably be able to get away with just using the free version. If you sell millions of copies of your game, you'll end up, the API will end up getting used enough that you're paying for it because you buy blocks of cloud credits and so on. So in terms of embedding our system in other systems, one thing we've tried to do, we've done, I think, good software engineering over the course of a long period of time, and so we have something which is easy to encapsulate. So one way of using it is to use our cloud. So you can just call our cloud. You can also have a private cloud. But another thing you can do is have a library version that is an embedded Wolfram engine. And so you can embed that engine inside other software. So for example, if you have that embedded engine, you can include it inside some program that's just a standalone program. And in fact, for example, one thing that's coming is an embedded engine running inside the Unity 3D game engine. Another embedded engine, there'll be embedded engines running inside spreadsheets and inside other kinds of programs, where those programs will be able to make use of the Wolfram language from directly inside that program. So another thing in terms of things that you can get that are kind of freely available, another big thing is we have a demonstrations project which uses this technology called CDF, computable document format. Okay, so this is just what's happening here is this is using a web plugin version. There's also a purely on the web cloud-based version, and I shouldn't have picked this example. I'll tell you what, let's look at the latest. Let's see what the latest contributed examples were. What looks interesting here? I don't know. Dissecting the net of a gyro. I don't know what the heck that thing is, but anyway, let's see what this does. Come on. I don't know why it's taking so long to load this. I'll tell you what, I'm going to just do that. Okay, so this is now I don't know what this does because I didn't. Oh, that's cool. Yeah, that's really quite cool. So this is something where this is kind of an open code environment, and we can look here at the code for this particular thing. And actually, it's remarkably short. I'm sure it's using. Hold on a second. Let me just make. It's probably making use of some extra initialization code up here. Oh yes, it's a little longer there. But so this demonstrations project is useful because it's sort of an open code thing where you can take code and make use of it in other programs. And we'll see, I think, a large expansion of this as the Wolfram language becomes available on the web. There's another thing which is the Wolfram community, which is actually a very vibrant place where, what is this? Let's take a look at this one as an example. This is a place where there's a lot of kind of interchange of, what is this? Somebody's asking, find polygons. It looks like they have this image and they want to make the different things out of separate polygons. And it looks like somebody here is suggesting how to do it. Let's see what happens at the end here. Okay, that looks good. Let's see what the person says. Okay, the person says thanks. That's always a good sign. And then there's more of this. But in any case, that's so there's sort of an ecosystem developing. And I think once the Wolfram language goes live on the web and so on, there'll end up being quite a community of people. I mean, there'll be sort of a marketplace for people writing code and being able to sell it to other people and so on. So that's yes, please. Go ahead. Yeah.
Are there any trusted language that you prefer to use, especially in the web technologies that you are computing some?
Sorry,
are there any trusted software or language that you trust more in your computation?
Well, as a person who creates languages, I'm
I know, I know, but are there any one that you prefer or think that it is more reliable?
Our language is, it's about 40 million lines of code. The very lowest level core is written in an extension of C. It has C++ code. It has Java code. The vast majority of the code in our language is written in our own language. In terms of things like, if you're asking about things like computer security kinds of things, if that's what you're asking about, that's not an area that we've been so particularly involved with, because it's an area we're going to get more involved with as we have more people using our cloud to do things. But I don't think I have a good answer to this question. If you give me a menu of languages, I probably could comment on all of them. Please, is there somebody over there?
I wanted to ask, where do you collect that huge amount of data? Is your company focused to collect those data or just for the computation?
Yeah, we have done a lot of work in collecting that data. I mean, we've worked with, we have data in thousands of different domains, and typically we work with whoever the primary source of that data is. In fact, we have every year, let's see, we probably have, every year we have a conference for people who are responsible for the world's large data repositories. And we've been basically the organization that's been most active in collecting different types of data and figuring out how to curate them and fit them together. I mean, you might think you've done 2,000 domains, that the 2,001st domain would be easy. Unfortunately, this is not the case. You get a lot of frameworks built up, and you can do a lot of cross-checking of a new domain against existing ones, but there are always new issues. And so, yes, this is a difficult task. One of the things that's interesting now is that the amount of data that we have is significantly larger than the text content of the web. And most of the data is not, it doesn't come from anywhere close to the web. It comes from databases, from raw databases that have been collected by governments, intergovernmental organizations, companies, sometimes amateurs, and so on. Go ahead, yes.
Now, one question I wanted to ask is if I understood correctly from the history of how you came about basically building Mathematica. Is it correct to say that you basically were interested in complexity, and now complexity arises from simple things, which essentially is chaos theory, if you can say that. And the field wasn't there, and that's why you decided to go to computation, and that's why we have Mathematica today?
You know, unfortunately, one's history is never as simple as. I mean, what I needed Mathematica as a tool to take the next steps in complexity theory, and yes, that's basically why Mathematica exists. Yes, but I mean, two things were true. That was factor number one. Factor number two was that in 1986, I realized that personal computers would, for the first time, be able to run serious computational software, and so that was it was an opportunity to build sort of a definitive system for doing that. And so it was both an intellectual objective and a market observation, so to speak.
If I can, I wanted also to ask something about still the knowledge base. Like, how do you compare them with? So you're saying that your database is, or your knowledge base is bigger than the collected data in the web. But like, how do you compare the potential, the stuff like Google knowledge base, the graph knowledge base that they have, where they do some semantic search? Like, how does that compare to what are you able to do right now, and where is this going in the near future?
So pretty much what Google has done is something that I told Sergey he should do 10 years before they did it, more than 10 years before they did it, which was take Wikipedia and grind it up and put the results on their search pages. They didn't want to do that because it covers up the ads. Okay? And after Wolfram Alpha came into existence, they decided maybe that was a good thing to do. But no, what they've done is just, I mean, all they're doing is kind of this kind of static entities and properties that basically largely comes from Wikipedia at this point. We've been interested in both taking sort of more primary data, and we've been interested in actually being able to compute answers rather than sort of just look up data. And so, you know, what we're trying to do is something vastly more ambitious. I think, you know, we've kind of proved that it's possible. It's, you know, for us, it's riding on top of a technology stack that we've been building for about 30 years. You know, most people who need that kind of computational knowledge have ended up using our, you know, our API. Google at present is not doing that. I think the kinds of things that we've done, possibly, you know, that work perhaps only needs to get done once, so to speak. We've tried to do it. I think you know, what we'll see in the actually the future is kind of frustrating because as we increase the amount of knowledge in Wolfram Alpha, the benefit of every incremental piece of effort that we put into increasing the knowledge is only a small percentage in terms of the number of queries. We can see this giant curve that stretches out for 20 years of what we need to add, and you know, every incremental piece of effort only moves the curve a small amount. But we will keep on doing it, and we'll gradually move this curve down. So, you know, as I mentioned, in math, we now have about 97% success rate for queries. We will get to similar levels in all other domains in time. It'll just take a lot of work and quite a bit of time.
Thank you.
Just quickly, there's a few more questions. I'm going to suggest we go on maybe about 5 more minutes, if that's okay with you.
I'm happy to go on for.
Okay, and then
I'll try to make my answers quicker.
But we can also stay here a while after, and so other questions can be asked.
Yeah, okay.
Okay. So,
I'll try and be faster here, but that's.
Thank you.
Yeah.
I am using Mathematica for a long time, and I quite used to Mathematica syntax. I want to understand the difference between Mathematica program syntax, the functions calling, and the Wolfram language.
Okay.
What is the difference?
Okay. Everything you know about Mathematica will still work in the Wolfram language. The Wolfram language has more stuff, quite a lot more stuff, but everything you already know will continue working. So that's the, so it's just, it's a, you know, it's a superset of Mathematica. So, please.
I have two short questions. First is related to Wolfram language. As far as I understood, it is very good at extracting information from data, extracting do some computation related to knowledge. So if I have collected some domain-specific data and want to extract some information from this data, so can it be used in data science?
Absolutely, absolutely. We think it's really a very, very powerful tool for data science. In fact, there's a whole product, data science platform that will be coming out.
So I can import my data and do some
computation? Yeah. I mean, right now it deals with about 300 different formats for data. And actually one of the most important things is we have a thing called WDF, Wolfram Data Framework, which is a canonical representation for data objects. So if you have, you know, like a city, there's a canonical entity specification, and we have natural language understanding, so we can take data that is given in essentially where the entities are specified in natural language and canonicalize them. So we think it's a really powerful tool for doing data science. I would say that at this point we are you know, up to a few gigabytes of data we can easily deal with. We are going to, you'll see over the next probably 6 months, we're going to take a series of steps. You know, the goal is a petabyte. We're not there yet, but you know, we're taking sort of a series of steps to get to being able to deal with data sizes like that.
The second question is more abstract, so it's about computational universe. So let's say all fundamental nature laws are extracted from nature itself, from our universe. So what do you think if we are trying to extract some laws from this computational universes? Is it not going to be artificial and not feasible?
Is it not going to be what?
Do you think it's not going to be artificial? So let's say when you extract laws from our universe, it's something that can be used in many things. For example, Einstein extracted all the fundamental laws in the universe. So relativity and other laws. But when you make your own computational universe and trying to extract some algorithms and data from this universe, don't you think it's something artificial?
I'm not sure I quite understand, but let me try. I mean, once you have the fundamental laws, you know, finding what the consequences of those laws are is almost infinitely difficult. So, like for example, even if we know, so a good kind of question would be, okay, we know the fundamental laws of physics. Is it possible to make a faster than light, you know, something that travels faster than light? It may be very hard to know that. It may be effectively undecidable from those laws. It may be that you can have an arbitrarily large, you know, there's no upper bound on how much computation you have to do to decide that. So that's one issue. So the other question is one of the, well, yeah, I think that's, I'm not quite sure I understood completely. It sounds like an interesting question, but I didn't quite understand it. Yes, please.
Hello. First of all, thank you very much for being here. It's really a good pleasure and honor. My question is more about principal problems and all the problems, and I would like to hear from you specification of these problems, on emerging problems that you can see that are principally solvable, and problems that are principally unsolvable yet. For example, by this I mean that first kind of problems are you rely heavily on algebraic computations, right? While there are some hopes to have some quantum computing that will change a little bit the game. And by saying principal problems, I mean that you in Mathematica heavily also use the symbolic language, right? But it is a verbal language. So, for example, you cannot talk with a dancing language, okay, or language of art. So it is a principal problem that's just impossible to say verbally. Okay.
Right.
Do you see any solutions to this, or what kind of problems do you see?
Okay, so I mean, there are two very different kinds of difficulty. One is more like computational irreducibility or undecidability. That is, you have a problem where you can state the problem perfectly well, but there's no finite amount of computation that can solve the problem. Okay, so one of the things that I think is true is that right now our mathematics and our engineering is very specially built to avoid irreducibility and undecidability. The things we choose to study in mathematics are things that carefully navigate around undecidability. When we just say, let's pick a math problem at random, it's much more common that we will wind up with something which shows undecidability. I think that's an issue. I think that kind of drives us to a more experimental approach to mathematics. In the case of studying natural phenomena, it drives us more to simulation than to kind of exact solutions and so on. That's one thing to say. It's interesting in building Mathematica, for example, let's compare solving equations over real and complex numbers with solving equations over the integers. Over reals and complex numbers, it's a decidable problem. Over the integers, it's an undecidable problem. The way that manifests itself kind of on the ground inside Mathematica is there's a single very powerful algorithm that will simply solve all real and complex equations. But for integers, there's 30 or 40 different algorithms that have to be put in to sort of patch different cases. So anyway, that's one sort of branch. The second branch is the question of sort of things that it's hard to represent symbolically. Well, clearly, one thing that I've been surprised by in building Wolfram Alpha and now the Wolfram language is the extent to which things you didn't think had any way of being represented symbolically actually are. Like for example, one thing we're going to, let's say human emotions or something. We may not be able to get the whole thing, but we will be able to get, the muscles in the face, and we'll be able to know we'll be able to interpret that as a quantitative thing, and we'll be able to probably have spaces of, this means it's some kind of emotional case versus some other kind of emotional case, and so on. What I think is going to happen is that we're going to see that a lot of these things, I don't know, like the aesthetics of color, for example, we know a fair amount about how to make that quantitative. We don't, I think what we're going to see is more and more of these things can be represented computationally. Now, people can make a bad model of our impression of how things work and say, that's not a good, but I think what will increasingly happen is these things will be able to be represented symbolically, and we'll be able to do some computations with them. And that's my expectation. Maybe if Bruce says we can do one. No, that's it.
Let's do one more question, and then afterwards, I'd like to say a couple of things, and then we can collect in the front of the room for a few minutes in case there are questions that haven't been asked. We can ask those as well. So we'll take one more question.
Right.
My honor to give you the last question, sir. So companies like Google, Apple, Microsoft, etc., they take private data from the users in order to make their products or the search engine better. Like Google uses the data of the Gmail account, Apple from the Macs, iPhone, etc. Does the Wolfram Alpha, the language, or even the search engines, anything that is made by the language, takes any type of information without the knowledge of the users and keep it in the cloud in order so your developers can use it later? Or is it better to say that dear users, we take them and you don't know?
Right. So we haven't, we're not running ads or anything like that. So we actually don't care very much about we're not trying to target particular users for particular purposes. We certainly look at the query stream from Wolfram Alpha. We need that because without that query stream, we have no idea how people think about stuff and so on. So we take billions of queries and we grind them up. Actually, one thing we've done, we're actually pretty careful about splitting the IP addresses and the queries very early in our process. And so we actually have no clue who asked which particular question. But we look at the aggregate of the questions. That's of great interest to us. We've also done some things. For example, we have a thing with Facebook where you can, let's take a look. Let's see whether I can show you some stuff. I'm just going to, So we have a, in Wolfram Alpha, you can connect it to your Facebook account, and it will give you a whole elaborate analysis of your, about where your friends are in the world and the distributions of this and that and the other. So we've had this for a while, and actually at first we collected, we had two cases. We collected absolutely zero data from users, and we had a box that you could check saying, I want to be a data donor, in which case we'll collect data. Okay, so we actually decided after a while that we would collect anonymized data from all users, and we tell people we're doing that.